So, with 1, 2, 3, 4, any questions?
Number 4.
Okay, number 4, good. There should be a big question on that. Anybody else? Everybody understands 3? Okay. Do you understand 1?
Yes.
Do you understand 2?
Yes.
Why was the oxygen not double bonded instead of the nitrogen? You did not just tell me that the oxygen is not the one double bonded because that's not what I drew.
No.
Okay.
The one in the reagent is not.
Why is that? Why is the nitrogen the one that's the nucleophile and not the oxygen? Nitrogen's a stronger nucleophile than oxygen because nitrogen is what? Less electronegative than our oxygen. Okay, so that makes it the stronger nucleophile. That's why the nitrogen is the one that attacked. Okay? And the third one. Okay, so if we follow the same patterns that we've been following all the way down, notice the nitrogen goes through and pretty much does what Jen referred to as a substitution for the oxygen. It's bad to refer to it as a substitution because it's not a substitution reaction. For it to be a substitution reaction, we're swapping sigma bond for sigma bond. This is a pi bond that's getting exchanged as well. So we shouldn't be calling it a substitution. We should think back towards what type of mechanism is occurring here. Okay? It's a complicated one because multiple things are happening. We're really doing 2 nucleophilic additions, or really a nucleophilic addition followed by an internal substitution, okay? Or even a nucleophilic elimination. Okay? But if we followed that pattern down to the third one, what would our logical product look like? We should have ended up with the double bond to the nitrogen. Why is that not the product? Well, number 1, that structure is not correct. To fix it, we need to make the nitrogen positively charged. Okay. Does nitrogen want to be positively charged? So what does it do? It steals electrons from the pi bond. But then that carbon becomes formally positive. And that's not a good thing. So what ends up happening? We take a hydrogen away to form the double bond.
So would you call it like an internal elimination?
It's kind of an internal elimination. It's also known as tautomerization. We are doing kind of a tautomerization there. Okay? Except we're using the nitrogen instead of the oxygen. So when we run through this reaction, what we end up getting is the one in red, not the one in purple. And the one in purple is bad because of that positive charge. Okay? So the structure will fix that by forming the double bond internally.
So if we go through the mechanism for 3,
Yep.
we would come to the purple.
You would absolutely arrive at the purple.
Okay, but it keeps going to form.
And it has to keep going to stabilize that structure. Okay? So when we go through and look at mechanisms, realize that, and it's not always true, but under most circumstances, we stop at a neutral species. Okay? Very rarely do we end a mechanism at a charged structure. Okay, so what does that mean? If we went to the purple one, it's charged. Is that stable? No, we have to continue to propagate our reaction and see, is there something else we could do? Okay, that's how we'd end up getting to the red one. Is that tricky? Abso-freaking-lutely. Okay, because how do we know to do that? How do we know to do that shift? It's really going to come from practice and recognizing charge stabilities. Okay? This structure, that red one that I got in the box, has a very particular name associated with it. Just like our very first structure has a name. It's known as the, I call it an imine. I don't know if that's actually the proper pronunciation or not. The imine sounds better, because, or I think it sounds worse, but it's more relevant to what it's spelled like. Okay. I don't have an amine down here because I don't have that doubly bonded nitrogen. What do I have down there?
Like the Enolate version.
I have the enolate version of the amine. Okay. So what are the two functional groups present in that structure? Okay. We can get more specific than a double bond. We can call it ene because it's an alkene double bond. So I have an ene, sorry, and I have an amine, and I have the enamine. It's what it is. I'm not making this up. It's actually true. You guys are all laughing like I made that up. No, that's actually legitimate. That's what it's called. Okay. Interesting feature about that. Those of you in lab might find this relevant for writing up your lab reports for the Wieland-Mischer. Why? You make an enamine in the Wieland-Mischer ketone synthesis. Proline reacts with the carbonyls to make an enamine. Okay. Enamines have very particular chemistry that is more selective than the carbonyl equivalent for our enols. Okay, and we'll see that a little bit later too. The last one. Hopefully you would have been able to pick out that that reagent was necessary, the di-NH2. Okay. Does everybody see that that is the reagent that we need there? Are there questions on that? Okay. So what I'm going to guess, Tanisha, your question was on is, what the hell happened in the second step that now all of a sudden everything disappeared?
Exactly.
Okay. So what do we see as reactive in that second step? Whoop, too far. I forgot. I got to actually draw this up. So if we draw this all out, I'm going to regret having drawn it here, but right? Different structure, but the same general idea. Right? What do we have reactive in that solution? So we have a pi bond between our carbon and our nitrogen, and we've addressed how that pi bond will react. How does that pi bond react?
It reacts by the electron moving up towards the nitrogen and carbon being more positive.
Okay. That pi bond is reactive where that carbon is now electrophilic. Okay. What else do we have floating around? What's that?
Long pairs.
Okay, lone pairs. What else?
We should the KOH.
We have KOH. What is KOH? A base, and potentially even a nucleophile. So we could run under the assumption that maybe that OH minus comes in and acts as a nucleophile. Okay. So before we panic and draw that, don't, because you don't want to. Okay. Does that match what we would see in our product? Why not? We would expect to see at least an oxygen bound to that structure in the product, and it's not there. So is the oxygen, is our OH acting as a nucleophile? No. Okay. So if it can't act as a nucleophile, I think I can do this. What can it act as? A base. Okay, well, where is there something basic?
The hydrogens of the alpha carbon.
So we could look at pulling hydrogens off the alpha carbon.
There's hydrogens on the nitrogen.
That is a possibility. There's also hydrogens on the nitrogen. If we pull hydrogens off the alpha carbon, do we really have a leaving group? No. Okay. So maybe we should try and pull the hydrogens off of our nitrogen. What would that result in?
Negatively charged nitrogen.
A negatively charged nitrogen. Is a negatively charged nitrogen a good thing to have floating around? No. So we would say, well, that's not very likely, except what can that negatively charged hydrogen do? How? How? But then what happens to the next nitrogen? It becomes... You exceed the octet. Ooh. So what do we continue to do, Corey? Keep pushing those electrons onto our carbon. Does carbon want to be negatively charged? No. So what could it do? It could pick up a hydrogen. From where? I have water floating around in solution. What's the result? Whoops. Sorry. Yeah? Is that any better than what we started with? Probably not, so we're probably looking at pretty steep equilibrium here. So as we've drawn, we're like, that's not really helpful. I don't see why that reaction would occur. Okay, but as Jen pointed out, we're closer. Okay, so likely what happened is someone mixed these chemicals expecting to see an oxygen in their product. They didn't get an oxygen. In fact, they lost all polar bonds in the structure. Like, what the hell happened? So they went back through and identified what the product was and said, okay, well, I know it disappeared. How could it possibly happen? Now they start working through a mechanism. We aren't at our final answer yet. Something else needs to happen. What is still present in solution? What can that base do? It can take off that hydrogen, off the nitrogen. The nitrogen would be negatively charged, but that's not good, so what can that nitrogen do? Resonance-ish by dumping that electron into that nitrogen, the next nitrogen. But now what's the problem with that next nitrogen? Somebody said it over here? It exceeds the octet. Okay, so what do we have to do? Keep pushing electrons. Well, I can only really push the electrons one step further, which then means, what do I have as a result? Whoops, not a resonance. I have a negative carbon, and you're right, the nitrogen's not attached. Do I want a negative carbon? What does it do? Pull off hydrogen from water in our solution, and we'd have our final product. So we say, okay, well, why? I formed two negative carbons. There's no way in hell I can form a negative carbon. That's not a likely thing. Sorry for pounding the table near the microphone. Okay. Why would this reaction occur? When we draw out our mechanism, typically what are we looking at? The organic compounds, because that's what we're concerned about in an organic chemistry class. But are other things produced? Yes. What were those other things produced? What can you tell me about the stability of N2 gas? Super stable. It is that last step of the mechanism that causes the whole thing to cascade through and completely remove the carbonyl because of the Chatelier. Everything else is equilibrium. That last step is now irreversible. So all the other steps can happen as slow as they possibly want. But the instant that compound is turned over with that irreversible last step, I'm now causing the Chatelier to continue to produce product. And it will always form in that forward direction. Okay? I may not like any of the mechanistic steps in between, but I have not invalidated Lewis rules. When I get to that final step, I go, oh, that's why. Thanks, chemistry. Why didn't you tell me that from the beginning? Okay. A lot of second semester is like this. We have to propagate it all the way through. Okay. It may not be apparent in the very first step. Questions? This reaction is known as the Wolff-Kishner Reduction. Why is it called a reduction? It may help if we erase everything. We lost bonds to oxygen, and we gained bonds to hydrogen. That's the definition of a reduction reaction. Neat, we have a new reduction reaction. Cool. We'll pick up a couple more when we move into chapter 19. That said, we still have to finish chapter 18. And there's the big whoa picture. Okay. So when we talked about carbonyls, or the ketones, we did the keto-enol stuff. Okay. Remember we said we had a nucleophilic carbon, and that nucleophilic carbon could react with bromine as an electrophile. It could have reacted as a nucleophile with our alkyl halides, okay, to generate a substitution. Okay. And then I said that we had all sorts of other reactions that could snowball out of that. Okay. And the reason they aren't, or we didn't discuss those yet, is that those were with a mechanism that we don't understand yet. What's happening in the bottom half? What is the nucleophile doing? What is our nucleophilic carbon attacking to form the left product? It's attacking a carbonyl in what type of a mechanism? A nucleophilic addition, which when we talked about our enolate chemistry, we didn't have nucleophilic addition reagents available to us. Okay? Now we do, because we're now introducing the nucleophilic addition mechanism. We now get access to all of those potential reactions. Is it any different than anything we've discussed before? No. It's exactly the same. Except every time we do a new one of these reactions, someone stamped their name to it super irritatingly. Okay? So we're going to run through a flood of 4 or 5 different named reactions that are all freaking identical. But just because they changed a functional group, they got to stamp their name to it. One of them I'm actually kind of excited for because it makes me look famous. So, the start of it all is our aldol chemistry. And this is really what drove everything. Okay? Any ideas why we might refer to it as the aldol? What am I starting with? An aldehyde. There's my ald. Okay. As a guess, what do you think is going to show up at some point in this reaction? An alcohol. Okay. So we're still looking at our enolate chemistry, so we're adding a good strong base. That base will deprotonate the alpha carbon, giving us our carbon nucleophile. Okay. Just for the sake of it, we could show in our curved arrows. Okay. Where we put the negative charge on our carbon. That was an acidic hydrogen because... Don't all shout that out at once. We can stabilize it via resonance. Okay. When I'm looking at those two structures and trying to decide how they react, so this is a fun thing, because I've been seeing people ask, and we look at those and we say, which of those two structures is best? Top or bottom? Why the bottom? Oxygen can hold a negative charge better. Which of those two structures should I look at to decide how it reacts? The top one. Your best resonance structure is what you should be drawing as your answer. But when I want to figure out how that structure reacts, I don't want to start from that one because it's low energy. It's not going to react. What I want to be looking at is the first worst or the least bad resonance structure. Second least bad resonance structure. That gets me the top one with the negative charge on the carbon. What do I now have with that negative charge? I have a carbon nucleophile. I also have base. I also have a base. Okay? Go figure. If I react a base with an acid, what do I end up with? A conjugate acid and conjugate base. Okay? What can I now do with that? Well, I could react that with any variety of electrophiles, or for that matter, acids. Is reacting it with an acid going to do anything useful? No, that takes us backwards. So that's not useful. I want to react that with something else. I want to react it with an electrophile. The potential electrophiles. Okay, we could have done bromine. Okay, we saw that in our first unit. We could have done, sorry, I just blanked. An alkyl halide. Okay, where one of our bromines and our carbon are our potential electrophiles. Okay, but that's doing substitution chemistry. That's some boring first unit stuff. We want to move on to our nucleophilic additions. To do a nucleophilic addition, what do I want to react it with? Both the alkyl halide and the bromine have positively charged species. Neither of those are doing nucleophilic additions. What does addition mean? Removal of a pi bond. So what am I probably starting with? How about a pi bond? But then I'd have an alkene, and how do alkenes react? As nucleophiles or bases. So what happens when I bring a negative near a negative? Nothing happens. Okay? So an alkene doesn't work. What other functional group has a pi bond? How about a carbonyl compound? How about a carbonyl compound that I started the whole system off with? What happens? The nucleophile can react with your starting or unnucleophilized, sounded kind of bad, aldehydes. What's the result?
Would you have to limit the amount of base then you'd have?
We'll bring base into it later. But yes, that is an important question to ask. Okay. So we would end up with that structure, where if we colored these in, so we can get an idea of where they came from, there's our starting aldehyde. Here's our nucleophilized. I really hope that word doesn't catch on.
Let's go down there now.
Okay. Where the new bond we formed, because that's not showing up quite as obvious as I thought it would, is this one in here. Is that a little bit better? Can we see those pieces now? Okay. Our purple nucleophilic carbon, if we go through and used an arrow, went through and attacked the electrophilic carbonyl, pushing the electrons up onto the oxygen. That's the result we get. Everybody got that? Is that structure stable? Charge. So oxygen can hold a negative charge relatively well, but is it all that great at holding a negative charge? No. So what do we need to do? We need to neutralize that oxygen somehow. How can we neutralize that oxygen? I can pick up a hydrogen from somewhere in solution, and I would end up with this structure. Let's take a closer look at that final structure. And you might guess it's not completely final. What is on the far right of that structure? The aldehyde. What is on the far left? Why do we call it the Aldol reaction? Because it was first discovered as a product of letting aldehyde compounds just sit on the shelf. Them just sitting on their own, they go through and make this species. Okay? They don't need a base to catalyze it. Okay? Remember, to form an enol, that's happening all the time. If base is present, we can speed the reaction up. So if I just have a jar of aldehyde sitting out, I'm going to make the aldol product. which is now an impurity in my aldehyde, so something I'd have to remove if I wanted to react just the aldehyde. Okay. Let's take a closer look at that structure. Is there another reactive site within it? Because we have to remember what else is still present in solution. The negative what? I still have the base. The negative carbon reacted, okay? But I still have base present. Well, why do I care about the base? I only care about the base if there's an acidic hydrogen. Do I still have acidic hydrogens? Yep. What could that base do? Take a hydrogen off, and I'd end up with... there's an interesting point. A negatively charged carbon. Is a negatively charged carbon stable? No. So I could do resonance, stabilizes it. Okay, like I did to begin with. That doesn't take me anywhere. Why would we not still just end up with that? Is there something else that it could do, Tyler?
Kids off. The OH is water. No. Yeah.
Well, if it's a base, then OH okay to leave by itself.
Is OH a good leaving group?
No.
No, but
We're in a base.
we're in a basic solution. So is the OH really all that bad of a leaving group? No. Okay. The only reason this step happens is if, and only if, what is a result? Well, actually, there's a couple big ifs in this. Number one, I have to have another hydrogen. I have to have that alpha hydrogen to do the elimination. If I do my aldol reaction and my aldol product, I do not have these alpha hydrogens, can I do the elimination? No. I have to have those. Okay? And even when we have hydroxide come off as a bad leaving group, okay, there has to be something driving the reaction forward towards that product. If hydroxide's a bad leaving group, I'm in an equilibrium between those two products, and yet I really only get this product. Why do I not see the aldol?
Is that because the OH comes off but then catalyzes other, no?
Nope. The OH as a catalyst needs to get regenerated anyway, so that's not going to be our issue. If all those other steps are equilibrium, and this last one is not an equilibrium step, why is it not an equilibrium? It's irreversible. For it to be irreversible, what does that mean our energy diagram looks like? That says that our product must be lower in energy than our reactant for that step. Well, why would it be so much lower in energy? Conjugation. The pi bond of our alkene is conjugated with the pi bond of the carbonyl. There is resonance now within that structure. That makes that product incredibly stable. I do not have that same resonance in the aldol, so I would expect that last step to occur. Everything, starting from the aldehyde all the way down to this species, is what is known as the Aldol reaction. Okay, because we're making an aldol. This last step is an extra step because that's not an aldol product. That's at best an alkene and an aldehyde. And they aren't even directly attached to each other. I mean, there's something in between. Okay, so what happened in that last step? There were more acidic hydrogens. Yes, that was an observation that allowed this to happen. What else happened? What was the other product?
Water.
Officially water. We removed a hydrogen and we removed OH. If we heated this reaction up, what do we end up seeing? We would end up seeing water vapor condense on our glassware, making this reaction a condensation. So if I now want to reference beginning to end, going from the starting aldehyde to this final product, I've run what reaction? An aldol condensation reaction. Okay, because we form an aldol that immediately forms the condensation. Okay. Can we get just an aldol reaction? Yes, if there's no alpha hydrogens. Okay. Can I get just a condensation reaction? Well, yeah, but then that has nothing to do with everything else we've done. Okay. So typically when you hear the word aldol, it is almost always followed by the word condensation. So when you're doing these, you need to be making that double bond. Okay, yes?
On the homework, you had this, but it said to give you the product before it was dehydrated. Did you know that?
What happened in this last step?
You lost the water.
We lost water. When you lose water, you would say you would be? There it is.
So you just want the aldol.
I just want the aldol. So there's only a couple ways we can get you to draw just the aldol. One is there's no alpha hydrogens, and you have to evaluate the structure. The second way is we explicitly tell you, don't do the condensation. Okay? Or we could say, give me the aldol product, not the condensation. Make sense? Okay. As a real quick review, let's kind of draw this out in the pocket because let's look for some cheats. How many of you want shortcuts? Okay. What did we end up with the product? What was our shortcut?
Cut double bond, or take double bond, and just connect.
Right? That was our shortcut. We got rid of the carbonyl and just connected the carbons. Anybody notice anything? Whoops. Get rid of those letters. Oops. So I drew in a different structure. Ah, stupid. The shortcut that we used for the Vidig, guess what? It's the same thing for the aldol. I wonder why. What type of mechanism was the Vidig? A nucleophilic addition. What type of mechanism are we doing for the aldol? A nucleophilic addition. Oh my God, we do the exact same mechanism, we get the exact same result. Yep, kind of cool. Okay? Questions? Oh, I can't erase yet. I'm gonna pause the video then, but
So
you'll have awesome notes.
for
The imine, I-M-I-N-E. Okay, and with that, now that I've started recording the video, I'm gonna pause the video again. Work through some practice. Okay, there's a lot of them up here. I'd recommend splitting it up. In fact, let's just go ahead and split it up. 1, 2, 3, 4, 5, 6, 7. There's 7. Which group wants to do the first 3 on the left? Okay. This side, you're doing the first 3 in the left column. This side, you will do the last 3 in the left column. Everybody will do the first one in the first column. Kind of make sense?
We do the first 3 and then the one by one.
Yep.
Okay.
So because Jen asked.
I get left and right confused sometimes.
That's Jen's side. Jen's side. Who is the easiest name?
You actually work one and you get confused.
Sean's got the easiest name, I think, that I could remember real quickly off the top of my head.
I've seen this spelled differently.
That's how you spell it, right, Sean? Yeah. Okay. Spend some time, work through it, see what you come up with.
On the board,
I will admit, Jen's side of the classroom, I'm pretty sure got the short end of the stick on that one.
Well, plus I'm looking at the one on the right.
if we look at our answer sets, for the far right, we get no reaction. Okay, and this is one that almost always throws students. Well, I got a negative oxygen, so I got to do something with it. Okay, well, it needs to react with the most positive thing. The most positive thing being? There is no acidic hydrogen. And I would end up with this structure. What is this structure? What was that? It is still a negative oxygen, so we could still even go, well, okay, we can pick up hydrogen from somewhere, from solution. What is this structure? You guys are responsible for knowing exactly what this structure is. It's a hemiacetal. What do we know about hemiacetals? They're not stable. What do they immediately do? Return back to the keto form, or carbonyl form. So yes, that chemistry is available, but it's not stable. I go right back to where I started. Well, crap. So what does that mean? There is no aldol because there is no alpha hydrogen. I need that alpha hydrogen. Okay? I need the electrons away from that alpha hydrogen position. So that upper right one has no real products to speak of. Okay? The upper left, okay, gets us, so if we go on now our upper left in just that column, that top one does get us a single product. We have an alpha hydrogen. We can remove that alpha hydrogen and use that to attack the molecule. And this is where we run into issues, because when we look at that, how many of each of those species are available in that first reaction? How many of that cyclohexyl carbaldehyde compound are there?
More than one.
Okay. Billions. Okay. And billions is probably a small fraction of it. We're probably looking in something on the order of 10 to the 10. Okay. So millions of billions or something like that. There's a ton of them there. And because the base that we're using is not strong enough to deprotonate every single one of those, what happens? I'm going to be left with some of them being a good strong nucleophile and some of them being left as is. If one is a nucleophile, let's take a look at what the other one has going for it. The other one has an electrophilic site, which is conveniently up in the blackness on the screen. So watch the video.
It's not on this
Oh, cool. Okay. Those two can now react with each other in the aldol fashion. To do the condensation, what do I need? I need another alpha hydrogen. Do I have a second alpha hydrogen? No. So what ends up happening? I get just the aldol, no condensation. So the question can be designed in such a way where you are not able to do the condensation. Okay. Does that mean the cheat doesn't work for us? No, we could still use the cheat. Okay. This needs to connect up. We'd say, okay, well that needs to become the double bond up to the carbonyl. Ooh, this is going to be fun because it's upside down. Whoops, except it's not a ring or not a benzene. Right? We say, okay, well there's my cheat. What's the issue with that cheat? I've exceeded the octet, which means I shouldn't have done the condensation. I can erase that bond and make sure I have the OH. Okay? Yes?
Could you also say that I can't do the condensation because I don't have an alpha carbon?
And Dana, you did it again. You're killing me. We talked about that. You shifted your carbonyl across.
Okay, we'll go through the
What was that, Tyler?
You can't do the condensation because you don't have an alpha carbon near the carbonyl.
Yeah, that's exactly what we said. Yeah. Okay. What happens when we move to the second one? Well, the second one has two alpha hydrogens. If I have two alpha hydrogens, what can happen? I can do the condensation. I have my 4 electrons to make the pi bond. I could now produce that one aldol condensation product. When I move to the third one, I end up with 2 products. Well, that's a bit interesting. What happened at the third one? Okay. my base needs to be able to deprotonate the alpha hydrogen. Is there an alpha hydrogen in that rightmost structure? No. So it can't deprotonate that one. That one cannot become a nucleophile. But what about the other one? It has 2 alpha hydrogens. So it could be turned into a nucleophile. To what extent is it getting turned into a nucleophile? Well, that depends on the strength of the base. The base isn't strong enough to entirely convert it, so what ends up happening? I get 2 products. One where I'm matching the exact same thing that happened above, the same type of system, okay, where it's self-reacting. And I get a second product where it's also reacting with the benzaldehyde. So I get 2 products out of that one. Will I get a condensation?
There's 2 hydrogens.
There's 2 hydrogens. So will I get a condensation? Yes. So both those products will undergo the aldol condensation. So that's already being like, I'm getting 2 products. That's not a good thing. Okay? But let's just see what happens if we move to the next one. And in the next one, where do I have alpha hydrogens? There's alpha hydrogens. There's alpha hydrogen. Oh, yeah, you're right. There's 5. Okay. So do I have enough to do the condensation? Yes. Which one is my nucleophile? Both of them are valid nucleophiles, which then means which one's my electrophile? Both of them are valid electrophiles, which then means I get every single possible combination, which gets me 4 possible products. And that is the nightmare of drawing that we made Sean do. Okay? So that sucks. We don't want to do that. Okay? So we want to devise an experiment or change the conditions where we prevent that. So what did I switch it up and do? I said, okay, well, I'm going to do it as 2 steps then. I'm going to do the base first with only one of them. This way I only generate 1 nucleophile. That's true. I only get 1 nucleophile, but did I get rid of my electrophile problem? No. I still have 2 electrophiles. So I'm still going to get 2 products. Well, crap. How can I set this up so that I only get 1 product? I need to make sure I have only 1 nucleophile and only 1 electrophile. The only way I can do that is I switch up the base to sodium hydride, or LDA, lithium aluminum hydride. What is special about the lithium aluminum hydride or sodium hydride? We talked about this when we looked at our enolates.
Is it maybe where it takes the hydrogen from?
Not really. They are our stupidly strong bases. They are 100% completely irreversible. What does that mean? I cannot form, or I won't have any left over of my carbonyl here. It will only be converted into the enolate. Once it's in the enolate, there is no electrophile, which means I'm only with 1 nucleophile. When I move on to the next step, all it can do is act as an electrophile. And I should end up with primarily 1 product. Okay? The aldol reactions have a nightmare of possibilities that can snowball out of them. So there are some big lessons that come out of this. We need alpha hydrogens. No alpha hydrogens, reaction doesn't work. Okay? We have to have the alpha hydrogens because we're doing that enolate tautomerization. Okay? As soon as we move to what is known as a crossed aldol, crossed because we're using 2 different ketone compounds or carbonyl compounds, okay, we get a nightmare of things coming out of this. Okay? I have to make sure only one of those species has an alpha hydrogen. If I've identified that, that should simplify the amount of species that can be a nucleophile. Now, only that species can be a nucleophile. Okay? I also have to look at or look at the base that I'm using for the reaction. Because if my base isn't strong enough, I don't completely shift to the nucleophile. And I have some of it left over that can self-react. Okay? I have to be very careful in the selection of base and the selection of reagents. Kind of make sense? These are challenging for that reason. Okay. After that, okay, what happens if I move to, say, a ketone? Where are there alpha hydrogens in this ketone? I get 4, okay. I can see your 4. And I'll raise you 6 more. Okay. Which I would really argue just means we're looking at 5. Why am I only looking at 5? Symmetry within the molecule. Does it matter what base I use and which one gets deprotonated? What happened if we used a stupidly strong base? We eliminated to form the kinetic product, which means where's our nucleophile? Yeah, you can roll your eyes at me, that's fair. Okay, we have our kinetic enolate versus our, and I screwed up the color coding again, so I'm going to rewrite that. We have our thermodynamic enolate. Why is it thermodynamic? What's more stable? The ene of our enolate is more substituted, so it is thermodynamically more stable. Okay. So depending on the base that I use, I'm going to get different locations being deprotonated. Okay. So I have to be careful when I have a ketone. Say like in the Wieland-Mischer ketone lab that you guys did Monday. I have to be a little bit careful about the choice of base because that can potentially affect how my reaction is going to run. Okay. Take it a step further. When we go through and look at this, oh, jerk, go away. That was at me, not at you. When we look at this structure, let's say we go through to deprotonate and we form our kinetic product. Where's our electrophile? The other carbonyl located within the molecule, meaning I have an intramolecular reaction or a ring closing reaction. What if I'd gotten the other one? Couldn't that have formed? Well, okay, why is that less stable? What we're looking at is not just the base we used, but also the product produced. If we do the thermodynamic product, we have 1, 2, 3, 4 atoms in our ring. That would be a cyclobutane. What can you tell me about cyclobutanes? Unstable, not likely to form. If I did the kinetic one, I'd have 1, 2, 3, 4, 5, 6 carbons. Which is more likely? The 6 carbon, and what I end up getting is the 6 carbon aldol condensation. Why does it do the condensation? I have more alpha hydrogen, so I'm allowed to do that second condensation, or that second step. Believe it or not, this now gets somebody else's name attached to it. Why? Because it's a ketone, not an aldehyde. So we really shouldn't call it an aldol anymore. We should call it a ketol. Why do we not call it a ketol? Because that would be confusing. So we call it an aldol, and we stick with that same functionality. Okay. Yes, conjugate additions. Okay. What happens if we go through and change our nucleophile? Instead of being just a standard enolate, okay, we switch it up and now move to an alpha-beta unsaturated ketone. Where's the enolate as far as its reactivity under our 1,2 or our 1,4 conditions? It is a negative carbon, but Grignards are negative carbons, and Gilmans are negative carbons, and yet they attack different locations. So where does the enolate fall? Pretty much smack dab right in the middle. Okay. So how do we know how it's going to react and where it's going to shift around? We tend to avoid them as much as possible for that reason. Okay? They tend to fall more on the Gilman side of things than they do on the Grignard. So our enolates will attack which position? The 4 position instead of our 2 in an alpha-beta unsaturated carbonyl compound, which then gets us to a new system. Now, of course, because this chemistry is brand new, it's not like it's a 1,4 addition with a standard carbon nucleophile, but because it's an enolate doing a 1,4 addition, we get to name it. And some jerk-off named Michael got to rubber stamp his name to it because, and not only just his name to the reaction, it's not just the reaction, he gets to stamp his freaking name to the reagents. It's a Michael donor because it's the enolate nucleophile. It's a Michael acceptor because it's a freaking alpha-beta unsaturated carbonyl. Seriously? That's why you get to stamp your name to it? Because you looked at it and said that carbon is also positive? Really? You saw resonance and you get to attach your name to it? Yes.
To be fair, they gave his first name, not his last name.
I think it is actually his last name. But aside from that. If we go through and take a look at the Michael donors, you'll notice not all of them are carbonyl compounds. But what do they all have in common? Polar pi bonds, because that's what this whole freaking section was about. Not carbonyls, polar pi bonds. Why do the polar pi bonds cause those to be good nucleophiles? Because of resonance, the electron withdrawing effect. Carbonyls just happen to be the classic example of it. Okay? But virtually everything in the donor category has resonance to stabilize that negative charge. Okay? So as long as you can make a nucleophilic carbon by deprotonating it, that's now known as a Michael donor. As long as you have an alpha-beta unsaturated polar pi bond, you now have a Michael acceptor. Okay? That's why we're classifying these as the polar pi bonds. Okay? With that, in 30 seconds, provide a mechanism. No, just kidding. We encounter enamines again. Why enamines? This brings up this question of 1,4 versus 1,2 again. We will talk about these again, I promise, on Monday. I just want to kind of introduce it and get it floating through there. Okay. We've got some things to discuss there on what's happening. Conjugate additions. Here's the other one I wanted to get. We got another stupid name attached to this. What's happening in that first reaction? And don't tell me Michael addition. We have a 1,4 addition reaction, nucleophilic addition. Okay, the base makes our enolate. The enolate attacks the 4 position. Okay, we end up with our 1,4 nucleophilic addition, just like we saw in chapter 17. Okay. Then what do we follow that up with? We add a strong base. That strong base reacts with the alpha hydrogen, making an enolate that then attacks carbonyl to give us the aldol condensation. So if I do a Michael reaction followed by an aldol condensation, 2 reactions that we've already attached a name to, but I do them step by step, I can now freaking add another name to it. Seriously? And what we'll find is that this chemistry shows up again, because what if it's not a carbonyl that I'm starting with? What if it's an ester instead of a ketone? Is that alpha hydrogen still acidic? Yeah. But now it's an ester functional group. So I'm not going to call it an aldol or a Michael or a Robinson. I'm going to call it a Claisen. Is any of the chemistry different? Fuck no. But we're going to attach another stupid name to it. Okay? That doesn't show up in this chapter because what do esters have different from our aldehydes and our ketones? What's special about that extra group? And the color coding might help here. It's not acidic because it's a CH3. If you remember, it's really only to my students. What was that? We have a leaving group, which means we'd be doing a nucleophilic addition followed by a nucleophilic elimination, which we officially haven't talked about. That's Unit 3. Okay? So that named reaction now we won't evaluate quite yet because it's a new mechanism. Okay? The lesson out of all of this, feel free to pack up. You're doing the same thing again and again and again, and believe it or not, again. Okay? You need to recognize the pattern. That will make it easier to deal with the reagents because it's the same chemistry through and through.